Hi everyone! Today we're going to be doing 2013 AP Physics problem number 2 of mechanics. And the problem is not here, but you can look at it on AP Central or on any website which basically shows the free response problems from previous years. This problem is the second one, and it involves a box of mass m being acted upon by a force A and a drag force. As I said, the problem, you can read it on a separate piece of paper, and it's moving at some velocity. So this is just going to be a walkthrough of how to do all parts of this problem. So first, we're going to start with part A. So this is 2013, number 2. Okay, so part A. Part A involves drawing the forces on the block, so basically a free body diagram. So, given what we know that here's the box, some dot, and we know that there's a force applied. So there's a force going this way, and then, of course, it's weight, and then it's normal force, which counteracts the weight. Now, this is basically shown in the diagram, but in the information that they give, it says that the friction between the box and the horizontal surface can be assumed to be negligible, but the box is subject to a drag force of magnitude kV. So basically, there's some sort of drag force, some sort of friction force acting against the force applied. So we're going to draw that here, and they said it's of magnitude kV. So we're going to call it kV. Okay, so that's actually part A. That's all you need to do for that part. So now we're on to part B. Now part B involves some calculus knowledge, but obviously if you're taking this test, you should have that knowledge ahead of time. But it says to write, but do not solve, a differential equation that can be used to determine the speed v of the box as a function of time t. So, for a differential equation, we always start with what we know. So right now, we always know that the net force is equal to ma. And we know that in this picture, the block is only moving in the x direction. So we're going to say the net force in the x direction is equal to ma. And based on what we drew in our free body diagram, we can substitute for the net force. And we know that the net force is equal to the force applied minus the drag force, kV. And that's equal to ma. Now, the part here is the part which requires calculus knowledge. And what we should know is the fact that A is the same thing as dv over dt. So now we can say that m dv dt is equal to force applied minus kV. So this is our differential equation. We want to solve for dv dt though, in terms of these variables. So we'll just divide everything by mass. So dv over dt is equal to force applied minus the drag force over mass. Okay, so that's the end for part B. Now on to part C. So part C asks us the terminal velocity of the box. And terminal velocity, this is what you should know with prior knowledge. But basically, terminal velocity is when you're on a parachute, is when your weight is equal to your drag force. So basically, the force in this direction is equal to the force in this direction. This is when, you're in a parachute, you're in free fall. That's what terminal velocity is. Terminal velocity. So, in this scenario, we're going to say basically the same thing. That the force applied, which is basically what's going in this direction, your force applied is equal to your drag force. This. right? And this is vt, or terminal velocity. So now we solve for terminal velocity, which is ft is equal to force applied all over k. And that's what you get. Oh, let me box the other answers right here. This is the answer for part B. Okay. So now on to part C, on to part D. And this is probably the longest part of the whole problem. So we're gonna do it on a separate sheet. So part D. Part D involves basically using the differential that we got in part B to get the speed of the box as a function of time t. So as we saw in part B, we got this equation, or this differential equation. So we're going to put this in our part D. So our differential equation again is m dv over dt is equal to fa minus kv. Okay, so in order to solve this differential equation, you need to do a separation of variables. But what you need to remember is that v and dv need to be on the same side. So this is how we're going to do it. We're going to take this whole thing, and we're going to go 1 over fa minus kv. So basically we took this whole thing and we brought it to this side, times dv is equal to 1 over m dt. So we took m, we brought it to this side, and then we took dt and we brought it to this side. So basically we just moved things around, but it's essentially the same equation. So now we need to solve for v, so we take the integral of both sides. So we get that, we get 1 over f of fa minus kv dv is equal to 1 over m dt. Okay, so now we need to put in our upper and lower limits. So as they said in the problem, they want it as a function of time. So you want to take this whole equation, or take this equation from 0 to some time t, right? So you're looking for the velocity as a function of time. So basically our bounds are going to be from 0 to t. And this is for t. But for v, our bounds are going to be from 0 to v of t, because this is the value at that certain time t. So we're just going to put some bounds on this. We're going to say 0 to v of t, 1 over fa minus kv dv is from 0 to t of 1 over m dt. So now we're going to need some calculus knowledge in order to solve this. And the way that you would solve this integral is by doing u substitution. And how you do u sub is the way I do it is I sort of give myself a sample problem. So I say, okay, this is sort of similar to 1 over, I'm just going to put some random numbers, 3x minus 5, right? So my kv is like my 3x, and my negative 5 is like my fa. So it's similar to that. And then I'm going to say my u is equal to 3x minus 5. du is equal to 3 dx. 1/3 du is equal to dx. So if I were to solve this integral, it'd be 1/3 1 over u du, or 1/3 ln 3x plus 5. Right? This is how I would solve this integral. So we're going to apply that same that same sort of like method we did to 1 over FA minus KV. So how we're going to do that is we're going to say, just like we did over here, we pulled out the coefficient, right? So we're going to pull out the coefficient. Sorry, that was meant to include just negative k. We're going to pull out the coefficient and put it under 1. So our coefficient was 3, and we pulled out a 1/3. Our coefficient is k, so we're going to pull out a negative 1 over k. And then ln, just like we did over here, ln, and then this whole thing goes inside. So ln FA minus KV, right? So just like this 3x minus, oh, this is supposed to be minus, I'm sorry. 3x minus 5 was here, and then 3x minus 5 got pulled here. So it's the same equation, just like, and we're doing the same thing here. We're taking the whole thing and we're putting it over here. So we're taking negative 1 over k ln f of a minus kv, and we're taking that from 0 to v over t. So we got this side done. And then for this part, it's just very simple integration. You simply plug t in so we have to integrate 1 over m. So it would be t over m from t to 0. Because 1 over m is a constant, right? Because m is a constant, so you're just adding another t. It's just simple integration. So t over m from t to 0. And so now we have this, and we have to solve this. So let's put in our upper and lower bounds. So we're going to say negative 1 over k. We're going to pull this constant out because it's not going to change whether what the bounds are. So we're pull this whole constant out. So negative 1 over k ln fa minus k times vt minus ln fk minus k times 0. Right, so we simplified this side, and we plugged in the bounds. So we know, okay, so I need another canvas. Okay. Okay, so we got this part. And so what we're going to do is we're first going to realize, okay, k times 0 is going to go to 0. Oops. K times 0 is going to go to 0. So basically, we're left on this side with negative 1 over k ln fa minus k vt minus ln fa. Right, because that goes to 0, so we don't count it anymore. So we got that, and now we need to simplify this side. So we're going to set that equal to, we plug t for t, so t over m, and we plug 0 minus 0 over m, which is basically t over m, so because this goes to 0. Okay, so then now we need to do some simplifying, and the way that we can simplify this is we have to use our rule of logarithms. So you say that negative 1 over k is equal to ln, and because of the rule of logarithms, this becomes f of k minus kvt, over f of a, and that all goes in sort of one big thing. And this is equal to t over m. So now we're going to rearrange some stuff. We're going to bring the negative 1 over k to this side. So ln, excuse my handwriting, minus k vt over f of a is equal to negative kt over m. And then now, oh, where'd my mouse go? Oh, there it is. Okay. Now what we're going to do is we're going to raise both sides to the e power because we need to solve for v of t, but we still have this pesky ln. We're going to raise both sides to the e power. Which, so we get, so raising e to the ln just gets rid of everything. So this becomes f of a minus kvt all over fa is equal to e to the negative kt over m. Okay? And then what we're going to do is we're going to simplify this left-hand side a little bit. So f of a over f of a is the same as 1. So we're going to say 1 minus kvt over f a is equal to e to the negative kt over m. And then we're going to add 1 to both sides. So I'm just going to move all of this here. So we're going to add 1 to both sides. So we're going to get negative kvt over fa is equal to 1 plus, negative 1 plus e to the negative kt over m. And because I just don't want a negative next to my v of t, I'm going to negate everything. So we're going to negate everything. So we're going to get kvt fa is equal to 1 minus e to the negative kt over m. Okay, so we're almost done. Now we just need to get vt by itself. So multiply by f of a, move it over here. So kvt is equal to fa 1 minus e to the negative kt over m. And then all you left need to do is divide by k. So vt is equal to fa 1 minus e to the negative kt over m all over k. And that's your final answer for this problem. It's a pretty long part D, but this is the answer that the College Board expects. So this is what they want. Okay, and then lastly for part E, can't find my mouse, there it is. For part E I think is pretty straightforward. They ask you, I think, they give you a graph, so I'll try drawing a graph here. So you have the graph, sorry, my drawing skills, v, t, and they want you to sketch a graph of the speed of the box as a function of time t, and explicitly label any intercepts or asymptotes, maxima, or minima. So what they want you to do is they want you to basically use the information that you thought of, or that you found out in the previous problems to solve this one. So first you should know that there is an asymptote. And where's that asymptote going to be? It's going to be at terminal velocity. Because when you hit terminal velocity, that's your maximum velocity. So you can't go higher than that. So we're going to put basically an asymptote right here, and we're going to say that's equal to fa over k, because as we saw in part 1, that was our terminal velocity. So we're going to say that's equal to fa over k. And then what you can do, or what I did for this problem for part D, is basically to sort of just, we got this equation in part D, part E. Part D got this equation. What I did was I sort of just plugged in random numbers because these are all sort of values, sort of constants, except for t. T is I plugged in the variable. These are all sort of values. And then I plugged it into my graphing calculator, and I saw what an equation like this would look like. And if you're not able to tell right off the bat just by looking at it, it actually looks like this. It looks like a logarithmic function, I believe. Yes, I think so. So this function also looks like that. My bad. So it's not supposed to hit the asymptote. The asymptote is supposed to be a little bit higher. But basically, it should look like that, and it should look like it's approaching terminal velocity, which is equal to F A over K. So that's how you do this problem. Thank you for listening.